Hello, everyone. So this narrated PowerPoint covers earthquakes, and it's kind of long. So what I'm going to do is break this PowerPoint up into two different narrated PowerPoints. And in this first PowerPoint, I'm only going to narrate the first group of slides that kind of give you background on the information that you really need to know. And then in a different PowerPoint, we'll introduce a case study where we'll look at effects and aspects of actual historical earthquakes. Okay, so what's an earthquake? An earthquake is ultimately ground motion. It's the shaking produced by fault rupture. And a fault is simply a fracture in Earth's interior along which movement occurs. So in this diagram below, the fault is the red line you can see right here. And then you can probably see these arrows. These arrows, and by the way, we're looking at a cross-section. These arrows indicate that the right side of the fault is shifting downward along the fault plane relative to the left side of the fault, which is shifting upward. The point on the fault plane where the earthquake originates is called the focus. That's right here. That's where the fault first begins to rupture. And then the point on the ground surface directly above the focus is called the earthquake epicenter. If we're making a map of earthquake locations, it's essentially an epicenter map. If we're looking at the actual location in Earth's interior of the earthquake in cross-section, then we use the focus. Okay, so ultimately, almost all earthquakes are produced by fault rupture. And then at your leisure, if you'd like to, you can look at some very interesting video footage of the Ridgecrest earthquake that happened last August. So these next two slides just cover a summary, essentially, of what you need to know from these two PowerPoint presentations focusing on earthquakes. So I'll kind of skip through them quickly. You can come back to these on your own. Okay. Well, when a fault ruptures in Earth's interior, it certainly generates heat along the fault plane, but more importantly, it sends out waves or pulses of mechanical energy that we call seismic waves. And there are different types of seismic waves with different properties, and these different types of seismic waves move at different speeds. The fastest seismic waves are called body waves, and they tend to travel in Earth's interior. And there are two different types of body waves, including P waves and S waves. P waves are compressive in nature. They're kind of like the way a slinky moves. And so as this P wave propagates from left to right in this diagram, the Earth's interior through which the wave energy moves gets kind of bunched up right where I've indicated. And then as the wave goes by, it stretches back to its original position. And then same thing here. There's where it's getting bunched up, and also same thing there as well. In other words, the bunching up, the compression is happening in a direction parallel to the direction that the wave itself is traveling. That's not true with S waves, which propagate by shearing. So in this case, the wave energy is moving from left to right, but the Earth's interior is actually shearing up and down at a 90-degree angle with respect to the direction that the wave energy is traveling. P waves are a little bit faster than S waves. The P actually stands for primary, and the S stands for secondary. And then there's another set of waves called surface waves that travel at Earth's surface. And so when P waves and S waves from the earthquake move upward and actually hit the Earth's surface from underneath, they generate surface waves in many cases. Surface waves come in two main varieties, including love waves, which are essentially like sideways S waves. They kind of move over the ground like a snake, shearing it back and forth sideways as the wave propagates forward. And finally, Rayleigh waves. Rayleigh waves are kind of like ocean waves as they're approaching the coastline before they break. They're these big rolling waves that you can actually feel during an earthquake. So these are just quick animations of P waves, S waves, Rayleigh waves, and Love waves. So remember that P waves are compressive, S waves propagate by shearing in a direction perpendicular to the direction the wave is traveling. Rayleigh waves are those rolling waves, those long rolling waves, and Love waves kind of propagate like a snake. They're kind of like sideways S waves. So this animation just shows the obvious relationship between earthquakes, which are the red dots, and plate boundaries, which are white lines. You know by now in the course that most earthquakes, of course, occur at or near plate boundaries. This is just an animation to remind you of that. So the next 3 slides go over some of the details of earthquakes as they occur at different types of plate boundaries. So here we're obviously looking at a subduction zone in cross-section. And what's interesting about plates, oceanic plates, when they subduct, is they kind of break up and crack up as they descend. And that breaking and cracking generates earthquakes as long as the lithosphere is brittle. And it remains brittle for a long time as it descends into Earth's interior. And so you can imagine that it's actually possible to map out the subducting plate in 3 dimensions by mapping out the locations of the earthquakes in the subducting plate in 3 dimensions. So as the plate descends, we of course get shallow earthquakes near the surface. We get intermediate depth earthquakes. Those are the green dots. And deeper than about 400 kilometers, we also get deep earthquakes. Important to remember that it's only at subduction zones where we get deep earthquakes deeper than about 400 kilometers. And the deepest earthquakes ever mentioned, ever measured, stretch down to about 600 or even 700 kilometers beneath Earth's surface, but not below that. Even though the subducting plate, in some cases, descends deeper than that, by the time it gets deeper than about 600 or 700 kilometers, it's sufficiently soft and plastic that it's no longer capable of brittle rupture, and therefore it's not capable of earthquakes anymore. So I wanted to show you as well this sort of interesting short video clip that demonstrates nicely what the relationship is between tsunamis, a type of tsunami called a seismic sea wave, and subduction zone earthquakes. So as that video clip said, very often large, damaging, catastrophic tsunamis occur at subduction zones where the upper plate sort of springs back towards the surface during the earthquake, and that pushes a bunch of seawater upward, and that hump of seawater, it then collapses gravitationally to send out tsunami waves in all directions. So just a quick diagram of the earthquake signature at collision zones. Here we tend to get shallow and intermediate depth earthquakes where 2 continental plates are converging. And at divergent plate boundaries, we exclusively get shallow depth earthquakes, quite shallow in fact, no deeper than perhaps a few tens of kilometers at the very most. And then at transform boundaries, we likewise get only shallow earthquakes. And as we've talked about, if we're out at sea and we're in between 2 mid-ocean ridge segments, like I'm drawing here in red, then the earthquake only occurs at the transform boundary in between the 2 mid-ocean ridge segments. Also, earthquakes at divergent boundaries tend to be small in comparison with earthquakes at convergent and transform boundaries. Quick concept check question. Which of the statements below is false? Let's go through these one at a time. A, most earthquakes occur at or near active plate boundaries. Well, that's true. B, deep earthquakes occur at all plate boundary types. That's the false statement. That's actually not true. So the answer is B, but let's just go through the rest. C, deep earthquakes occur only at subduction zones. That's true. D, only shallow earthquakes occur at transform and divergent plate boundaries. That's true as well. And finally, the point on Earth's surface directly above the earthquake focus is called the epicenter. That's true as well. So B is the right answer. Here's a quick clip to demonstrate to you how the instrument works for actually measuring seismic wave energy. This instrument is called a seismograph. And when we have the earthquake waves essentially shake every part of the seismograph except for this pen that sort of hangs down, drawing on this rotating drum. The pen is suspended to a heavy or connected to a heavy weight, so everything moves but the pen. And essentially what we get is a strip recording of the earthquake. We read this strip recording from left to right, just like we would a line of text. Remember the primary waves we talked about a few slides ago? Those are the P waves. They arrive first, so they're going to be on the left, followed by the secondary waves, the S waves, followed after that by the surface waves, which would include both Love waves and Rayleigh waves. This diagram looks more complicated than it is. You do need to know it, so spend some time in this diagram. I'll just briefly go through it here. So the actual strip recording itself is referred to as a seismograph, or rather a seismogram. That's what I meant to say. And as I mentioned before, it's just a strip recording produced by the seismograph. It represents a permanent record of the actual earthquake. So time is going to be read from left to right. Earlier times are on the left, later times are on the right. And as we talked about before, the first set of squiggles to arrive are the P waves. The next set are going to be the S waves, followed lastly by the surface waves. Three measurements you need to know how to make in general on this diagram. One is simply what's called the amplitude. It's the deflection from the background reading. On this seismograph record, this is the background. This is the zero line. That's the line being drawn on the drum or on the computer screen before the shaking starts. And then once the shaking starts, the pen will either be deflected upward or downward as the waves arrive. When the ground shakes in one direction, the pen goes up. When it shakes in the opposite direction, the pen goes down. So if we're measuring wave amplitude, then we always start from the zero reading and we go up either to the top of the tallest wave or the bottom of the tallest wave underneath the zero line. Again, there's nothing special about whether we go up or down. That simply tells us which direction the ground is moving, one way or the other. So this is just an example of how we might measure the amplitude of the largest P wave. This is an example of how we might measure the amplitude of the largest S wave. And finally, this is an example of how we might measure the amplitude, that is the deflection from the background of the largest surface wave. Okay, so make sure you understand how to measure wave amplitude on a seismogram. The next measurement is called wave period, and that's just the amount of time it takes for the wave to complete one cycle, from the beginning to the end of the wave. And a convenient way of measuring wave period on a seismogram record is just to measure from either trough to trough or peak to peak, and it doesn't matter which we pick. So this would be the period of the P waves, this would be the period of the S waves, this would be the period of the surface waves. And essentially what wave period tells you is how rapidly the ground is shaking back and forth. When P waves arrive, it's almost like a buzzing or a very rapid back and forth vibratory motion. When S waves arrive, the ground shakes back and forth a little bit more slowly, in the sense that it takes longer for the ground to return to its initial position, and surface waves shake the slowest in the sense that it takes the longest for the wave to make one complete cycle. Generally, it's surface waves that cause the most damage to buildings, because surface waves tend to have larger amplitudes in comparison with P waves and S waves. So in summary then, make sure when you're given a seismogram record like this that you know how to measure wave amplitude and also wave period. One last measurement that's important is what's called the S minus P time interval, or delta T. That triangle symbol there is the Greek letter delta. And the way we measure it is from the beginning of the very first P waves right here to the beginning of the very first S waves. And we're measuring a time difference, because that horizontal axis is time. As we'll see in subsequent slides, that's an important measurement to make, because we'll be able to use that measurement to ultimately locate where the earthquake occurred. So here's how we go through the process of determining the earthquake epicenter. And it's based on the idea that P waves travel faster than S waves as they propagate outward from the focus of an earthquake. And so we can make a graph that shows the gap in time between the P waves and the S waves. And the important thing here is that as you get further and further from the source of the earthquake, the gap in time between the arrival of the first P waves and the first S waves increases. So let's do an actual example here, and you'll see how to take the information on a seismogram to determine how far away the earthquake occurred. So in this example, I have my seismogram record, and I make a measurement on it, and it just so happens in this case that my measurement of delta T is 40 seconds. That means there's a 40-second gap in time between the arrival of the first P waves and the first S waves. So I go over to my graph over here, and I find my delta T of 40 seconds. And then I'm going to run over to the S minus P timeline. And then from there, I'm going to run straight down to the distance axis and figure out, in this case, that a delta T of 40 seconds means that my seismograph station is set up 400 kilometers away from the earthquake. So in general, and hopefully you can see this by now, both in the graph and just conceptually, that as delta T increases, as the gap in time increases between the first P waves and the first S waves, the distance to the earthquake increases. So let's do a quick concept check. Study the station A seismogram below. That's this one, obviously. And use the delta T value together with the time versus distance graph to determine how far away the earthquake occurred from station A. So I'll give you a couple of seconds to do that, and you can probably do it, by eye. Okay, so what do you think? Is the answer A, B, C, or D? Well, let's see. So our measurement tells us that our delta T value is 30 seconds. So we're going to go to 30 seconds, and then like we did in the previous slide, we're going to go straight over till we hit the S minus P line, and then from there we're going to go straight down. And it turns out that a delta T value of 30 seconds corresponds to just under a distance of 300 kilometers away from the earthquake. So A is the answer. Okay, now we're going to move on to a new concept, and that is how we measure the size of earthquakes. This is with a measurement known as earthquake magnitude. And it essentially refers to the amount of energy released during the earthquake. The important thing about earthquake magnitude is it's reported as a single number for any particular earthquake. It doesn't matter how far away we are from that earthquake, the magnitude of that earthquake is always going to be the same. So for example, even if we get a high magnitude earthquake of like magnitude 8 on the other side of the world, by the time those S waves and P waves and surface waves reach us here in San Diego, their amplitudes might be really, really small. We might barely feel them, or we might not even feel them at all. That doesn't mean the waves were generated by a small earthquake in this case. It just means that the earthquake, a high magnitude earthquake, was very far away. Historically, the first magnitude scale ever invented was the so-called Richter scale, which you've probably heard of. This was developed by a seismologist at Caltech here in Southern California by the name of Charles Richter. And Richter based his magnitude scale on the maximum amplitude of a seismic wave recorded at a distance of exactly 100 kilometers away from the earthquake. Now, we won't go into the details about how he actually did that. Obviously, the seismograph that he's using to measure the earthquake probably is not going to be located exactly 100 kilometers from the earthquake. So how did he get around that? It's actually easy. It turns out there are mathematical ways of sort of shrinking or stretching wave amplitudes to correspond what they would be if they did originate 100 kilometers from the earthquake. But in any case, that's what we're going to go through in the next couple of slides, how to determine Richter magnitude and actually locate the, determine the location of an earthquake of a certain Richter magnitude. Typically in the scientific literature, Richter magnitude is represented with a capital M and then a subscript L. L stands for local in this case because Richter's original magnitude scale was only meant for Southern California earthquakes, and it was only subsequently that it was applied to earthquakes around the world. Nowadays, though, since roughly the 1970s, we have better earthquake magnitude scales than Richter's original scale, and the best one nowadays is what's known as the moment magnitude scale. Again, we're not going to go into much detail about moment magnitude, but the only thing I do want you to appreciate about moment magnitude is that it's ultimately based on physical aspects of the earthquake, like the area of fault slip, how much the fault slipped and how rigid the rock was that slipped to create the earthquake. The Richter scale, in contrast, is what's known as an instrumental scale, and that just means that it's a parameter that we can determine from an instrument. It doesn't necessarily correspond to an actual physical measurement or series of measurements like the moment magnitude scale does. Okay, so we're going to get some practice here determining Richter magnitude. So step one, and we're going to do this using a seismogram record. So step one is to find delta T. And this, by the way, is an example earthquake. So in this case, delta T corresponds to 24 seconds. Step two is to find the maximum S wave amplitude. And in this case, that corresponds to about 23 millimeters. Again, measured from the zero reading of the instrument up to the top of the tallest S wave. Step three then is to plot the delta T value on the left-hand scale. That's the delta T scale. And amplitude is going to be plotted on the right-hand scale. And in this example, we're going to do this using red dots. So there's the point on the delta T that is the S minus P time difference scale corresponding to 24 seconds. There's the point on the amplitude scale corresponding to 23 millimeters. And The last step simply involves drawing a line between these 2 points. It's in blue, but I'll highlight it in red. And if we were really doing this, we'd use a straight edge. And where that line intersects the middle scale gives us the magnitude, the Richter magnitude of an earthquake, which in this case you can see is magnitude 5. So Richter created this graph as a simple way to determine earthquake magnitudes, again, just for local Southern California earthquakes. So it's your turn now. So see if you can analyze the above seismogram record right here to determine the Richter magnitude of the earthquake that produced this seismogram record. I'll give you a second to do that. Did you get the answer? This is very similar to what I might give you on an exam, by the way. Well, the answer is magnitude 4. And let's quickly see how we get that answer. So we know that delta T, in this case, again, from the very beginning of the P waves to the very beginning of the S waves, that's 10 seconds. So that number is going to go right here. And the amplitude of our S waves, in this case, is 20 millimeters. That number is going to go here. And then we're essentially going to connect a line between the two, and that line intersects the Richter magnitude scale at magnitude 4. So I'll get rid of all the red ink here. And that's essentially what we just did. So make sure you can do that. I'm actually going to give you some practice doing this in a short exercise that I'll be assigning. So imagine then if we went through the process of determining how far away the earthquake was from a certain location, if we did that exercise 3 times for 3 different locations, you're also going to get a chance to do that. And so if we know that the same earthquake at 3 different locations is obviously different distances from those 3 different locations, then those different distances each becomes the radius of a circle. And when we draw our 3 circles on the map, where the 3 circles intersect gives us the epicenter location. This is a process called triangulation, and you're going to get a chance to do this. Okay, one of the interesting things about earthquake energy is it increases dramatically with increasing magnitude. The magnitude scale is what's called an exponential or a logarithmic scale, and that just means that higher magnitude earthquakes release way more energy than lower magnitude earthquakes. And in fact, we can add some numbers to this. For each 1 point increase in earthquake magnitude, so we go, for example, from a magnitude 3 to a magnitude 4, 32 times more energy is released. Well, what if the jump is even greater? What if we go from a magnitude 3 to a magnitude 5 earthquake? How would we calculate how much more energy is released? Well, all we do is we take the difference between the 2 earthquakes, the difference in magnitude, which of course is 2, and then that number 2 becomes the exponent to the number 32. And if you're a little bit rusty on exponents, 32 squared doesn't mean 64, it means 32 times 32. And that number is equal to 1,024. In other words, by only going up 2 points on the Richter scale or the moment magnitude scale, the amount of energy released increases by 1,000 times. That really drives home the point that larger earthquakes release way, way more energy than smaller earthquakes. So you get to try now. A magnitude 4 earthquake releases energy equivalent to 56,000 kilograms of explosives. How many kilograms of explosives would correspond to a magnitude 6 earthquake? I'll give you a second to pick what you think is the right answer. Okay, let's go through it. Well, the answer is 3. By going up only 2 points on the Richter scale or the moment magnitude scale, we release 1,000 times more energy. So 56,000 times 1,000 is 56 million. And again, all we do is we take the difference in magnitude between the two earthquakes, in this case 6 minus 4 equals 2, and then we just raise the number 32 to the second power. 32 times 32 is about equal to 1,000. We'll round it to 1,000. And so we multiply our original energy release, 56,000, by 1,000. And if you crank it out on a calculator, you get 56 million. Okay, last slide in this presentation is a summary of what's called earthquake intensity. And earthquake intensity is different than earthquake magnitude in the sense that it's a descriptive scale, it's not a mathematical scale, and all it really tells us, all it really seeks to capture is a descriptive measure of earthquake damage at, as a result of a particular earthquake. So for example, at intensity 1, we wouldn't even feel the earthquake. At intensity 4, you know, it might be felt by many, but we would characterize the shaking as light. But you can see when we get up to larger intensities, say even severe or violent, then you know, we're talking about considerable damage. So two main differences between earthquake magnitude and earthquake intensity. Earthquake intensity is a descriptive measure of the earthquake. It's not a mathematical or a number-based measurement. And also, more importantly, earthquake intensity changes depending on where you are in relation to that earthquake. So you can have many different intensity values for the same earthquake. If you're far away from the earthquake, you can expect lower intensity values. If you're right on top of the earthquake, particularly if it's a high magnitude earthquake, you're going to get very high in intensity values. So we will go ahead and stop there, and then we'll proceed to the next PowerPoint.